Thank you everybody for joining this call. And I'm Piero. I'm from Uber AI. I actually have been working at Uber up until last Monday. So now I'm not an Uber employee anymore. I should change the slides. But what I'm going to present you is Ludwig, which is the tool that we're going to use for the hackathon. It's a generic deep learning tool that allows you to train and use deep learning models without writing code. But so it's not only an NLP tool. It can do many other things, and we're going to see some examples of that. But it has some developed NLP capabilities. So I'm going to show you some examples on how to use it for doing NLP too. So it's particularly good for experimentation because, as you're going to see, it allows you to swap in and out many different deep learning architectures and allows you to solve many different machine learning models. It is based on TensorFlow, and you actually don't require code to use it, but there is also a programmatic API that you can use it that basically will allow you to train and use deep learning models in really few lines of code. I'm going to show you. These are some statistics. It's been pretty successful after like a year and something after its release. Pretty successful on GitHub with 6,700 stars. And I hope you're going to like it and also add your own stars to that, I guess. And with also more than 1,600 downloads a month. There's more than 60 contributors, although the main contributors is a small set of those. So I would say 5 or 6. And there's more than 80 commits a month, so I'm working a lot on it. These are some of the companies that are using it at the moment. There's also some universities that are either using it or planning to use it as a tool for teaching. And also some companies have built some integrations within Ludwig. These are the general principles of design principles that I tried to follow when I developed Ludwig. First of all, I wanted to make a tool that was general, which I tried to achieve with a new level of abstraction that is based on data types. And this level of abstraction that we're going to dive deeper into allows for a general design that maps to many, many machine learning model problems. I also tried to make it flexible so that both novices and expert users can find value in using it, and also tried to make it extensible so that when there's a new model or a new architecture that comes out that's super powerful, then it will be pretty easy to add it to Ludwig. Deep learning models are also usually considered black boxes, but I wanted to try to make the models that you train with Ludwig as understandable as possible. And in particular, I provide a bunch of visualizations that allow you to check and visualize both the performances of the models and the predictions that the models produce. I also try to make it as easy as possible. And finally, we released it as open source under Apache License 2. Let's start with a simple example. So let's assume that we have a table that contains 2 columns. One, it's the header is news, and the content is text of those news, the body of those news. And the other column is called class and contains which class is associated with this news. So what we want to do is to train a model that from this data allows to learns to recognize which class is associated with a specific news. And when you have a new piece of news, it can predict a class for that piece of news. This is what you have to do in Ludwig to train such a model. You have to call the command Ludwig experiment --data CSV, which is the path to the CSV files that contains that data that we've seen before. And you have to provide the model definition, which is really the core of Ludwig, -- model definition. And in this case, you provide a string. This string contains YAML, which is let's say data format that is human readable. It's pretty simple. And in this case, you can see that the model definition is a dictionary that contains, in this case, two keys: input features and output features. Those two keys have values that are lists, so you can have multiple input features and multiple output features. In our case, we only have one element for the input and one element for the output. The element for the input is a dictionary with name equal to the value of the header of the column in your data that is the input, and a type, in this case text. For the output feature, we also have a dictionary with name class and type category. Basically, what we're telling Ludwig is we are declaring, given these inputs, news, produce me these outputs, class. In some cases, the model definition can become a little bit longer, and so instead of specifying a string, you can specify a file that contains the YAML. And so in that case, you will use model definition file instead of the model definition. What happens when you call this command? Ludwig first splits the data in training, validation, and test sets, or you can also provide the splits already produced if you want. Then it trains the model on the training set, validating on the validation set for early stopping or for figuring out some hyperparameters, and then finally predicts on the test set. And so this is what you're going to see after the first epoch. You see Ludwig first trains and then evaluates on the training, validation, and test, and you have this table that contains the performance of the model. It contains the loss, the accuracy, and a metric called it's3 on all the three splits: training, validation, and test. After a few epochs, in this case epoch 4, you'll see that the performance increases and we reach peak accuracy on the validation set. And then after a few more epochs, we didn't get more performance on the validation set, and because of that there's early stopping. So Ludwig stops the training and returns the model that was the one with the highest accuracy on the validation set. At the end of the process, it runs a full evaluation on the test set, and what you obtain are some statistics that are overall, like this accuracy, it's at K, and like confusion metrics. But also you will have some statistics that are specific for each class that you have in your classification problem. So this is basically one example of what Ludwig can do, one specific problem that you can solve with Ludwig, text classification. But now we're going to see how does it work and how many more things it can do. Do you have questions so far?
Unmute myself. So I will, how do we take the questions, Piero?
I guess.
See the chat forum?
Yes, I guess if people write in the chat.
Okay,
then
so far I see no questions, but I can post here now. So just a minute, I will post here now. Any questions?
Got it.
And let's see who, if somebody shows. If not, then we can continue. And I will mute myself. Okay, so nice and clear so far from Garrett. So thank you, Garrett.
Let's go on then.
Garrett.
All right, so how does it work?
Good, so we'll proceed, yeah. I'll mute myself.
So the training works this way. It's pretty standard. You have some input data, in this case, a CSV, and there is a pre-processing step that takes that data and creates some mappings and saves them into a JSON format. Those mappings are important because they are useful for transforming data into tensors. And when you have new data, you're going to use these mappings to map the data in the same tensors. For instance, one of the mappings is if you have category, then you will map from the string of the category to an integer that is a number that is going to be there in your tensors. So after the preprocessing, what you have is tensors, for instance, in NumPy format. And these tensors are going to be provided to the model training that ultimately produces a model with its weights and its hyperparameters. At prediction time, what happens is that you have some new data, so a new data CSV, and you're going to reuse the mappings that you obtained during training for performing the preprocessing and obtaining some new preprocessed data that is provided to a model for obtaining predictions. And the model is loaded from the weights and the upper parameters that we obtained at training time and produces some predictions and scores in a raw format, raw numerical format. And then we have to process this data using, again, the same mappings that we obtained during training to obtain the final predictions in a CSV format. And the experiment command that I showed you before, what it does is does first the training and then the prediction, one after the other. And so the experiment command, given the CSV, produces the weights, the upper parameters, and the mappings, and also provides with the final predictions on the test set, together with training statistics and test statistics in JSON format. All these files can be provided to the visualization component to obtain some graphs and some visualizations. So what actually happens under the hood when we run the experiment command, and how can we modify the model definition to address different tasks? So the magic of Ludwig lies in three main things. The first one is the data type abstraction, and we're going to go deeper now into it to show you how powerful it is and what it allows you to do. The second one is the declarative model definition. As we've seen an example of it, it allows you to just declare what you want without actually writing code for how it's going to happen, how the model is going to be built, and how the training process is going to happen. And finally, there's a smart use of KVArgs, which is a Python construct you may be familiar with, which allows you to provide parameters to a function that are collected in a dictionary with their names and their values. And this basically allows you to provide parameters from the model definition that go all the way into the code and all the way to the, that allows you to change all the little details of the code. So you have full control of what's happening at the lowest level. So if we go back to our example, this part highlighted here is the model definition. This model definition that we provide is actually merged and overrides some default model definition. And so this is actually what Ludwig ends up using. It seems big and complicated, but we're going to go into details to show you how to modify all of it and to govern it, basically. It's divided in 5 different sections. Input features and output features, we've already seen an example of that, but we're going to go more in detail. But there's also an additional component called combiner that I'm going to explain in a minute, and 2 more components, one for training and one for preprocessing. Training and preprocessing allow you to, for instance, explain, modify the behavior of the training loop and, for instance, change the batch size or change the learning rate. And the preprocessing allows you to explain to the mod to Ludwig how to perform preprocessing on your data, so you have full control. But let's dive deeper into input, combiner, and output. This is the basic architecture of Ludwig. You have different data types. We have seen an example with text and category, but there's many others. For instance, there's numerical, binary, sequence, vector, sat, bag, image, time series, audio, H3, which is geospatial data, and date. And you have similar data types in the input, even not all of them are yet available. And the reason why you need a combiner, which is a component that takes more than one input and produces one output, is because you can have multiple inputs of different types, and you need a mechanism for combining the information coming from them into information that then is used for producing an output. And so different instantiations of this architecture allow to solve different machine learning problems. We've seen an example where we have one text input and one category output, and you obtain a text classifier. But if you have, for instance, an image input and a text output, you can have an image capturing system. Or you can have category, numerical, and binary as input and numerical as output, and you have a classic regression system. Or you can have speech as input and binary as output, and you can have a speaker verification system. Or you can have text and image as input and binary as output, and you can have a visual question answering system that can answer yes or no questions over images. And you can imagine that depending on the different types of inputs and outputs that you have in your problem, you can solve many, many different problems by just combining different types for both inputs and outputs. Moreover, each input type can have multiple encoders to choose from, and each output type can have multiple decoders to choose from. The idea is that these encoders and decoders are functions that take the raw tensors and manipulates them into some latent representation for the inputs, for the encoders, and for the decoders are functions that, taken the latent representations, produce and generate outputs. One example of that is the text input feature. These are the encoders that are available in Ludwig right now. And as you can see, basically all of them take as input either words or characters, actually the tensors representing words or characters, and they all produce a vector encoding at the output. And then the internal part is different because the stacked CNN, for instance, uses several 1D convolutions and two fully connected layers. But the parallel CNN uses 1D convolutions in parallel and then follows them with fully connected layers. We also have a stacked parallel CNN when you have the parallel CNN repeated more than one time. Then you can have an RNN that can use different cells like LSTM or GRU, and then a combination of the two. So a CNN followed by an RNN. And we also have support for BERT and with like some layers of transformers followed by fully connected layer. If you want to use either of those, this is the part of the model definition you have to put when we provided the information for an input feature. We've already seen that you have to provide the name and the type. Moreover, you can also provide the encoder. And so each encoder has a name, and you just provide the name of the encoder, and you're good to go. In the case of text, you can also provide word or char for using splitting word, the text by words or by characters. Each encoder has its own hyperparameters. Here in gray, you see all the hyperparameters that you can change for the parallel CNN. And these are the default values. So if you don't specify these parameters, it's going to use the defaults. But you can change them as much as you want. For instance, you can change the embedding size, or you can change the number of filters, or you can change the number of fully connected layers, their size, which activation, which norm, if to use dropout, and so on and so on. So you have full control. And the nice thing is that if you want, this is an example of what I was saying with KVRs. Basically, this is the class that implements the parallel CNN. And if you look at the parameters of the init function of that class, those are one-on-one mapped with the parameters that you have access to from the model definition. And this means that those parameters go all the way down from the model definition to the actual code implementation. The nice thing is that if you want to use the stacked CNN, all you have to do, you just have to change the encoder keyword to stacked CNN, and everything works right away. You have also some parameters, and these parameters may be different from the ones of the parallel CNN, but you have full control over them. And the same is true for the stacked parallel CNN, for the RNN. As you can see here, the parameters for the RNN are very different. For instance, the cell type, bidirectional, or the state size, which are different parameters. But again, in order to use it, you just have to change the encoder RNN, and that's all you have to do. And the same is true for CNN RNN and for transformers too. The nice thing about this architecture is that it allows for a lot of code reuse. And so all the encoders that I use for text can also be used for sequences, time series, and audio. For image features, on the other hand, we have only two encoders at the moment. One is a stacked CNN, which is similar to VGG, if you're familiar with that. And one is a ResNet. And again, you can provide all the parameters of these encoders. For numerical and binary features, the way we encode them is really simple. For numerical features, there is one fully connected layer plus norm, which is used for scaling, but you can also decide not to use it. And for binary features, they just cast the two floats and use as they are, really. Category features can be encoded in two ways, either as dense vector or sparse vectors. Dense vectors have an embedding matrix followed by fully connected layers, and sparse as a one-hot encoding followed by fully connected layers. In the end, you always obtain a dense vector. There's also sets and bags features in Ludwig, and they're both encoded by using an embedding and then an aggregation over this embedding. The aggregation is different between set and bag because sets only have elements that appear once, and so the aggregation can be just a sum or an average of the embeddings of the single elements. But for the bag, we have a weighted aggregation that depends on the number of times the element appears in the bag, and then after that, you have fully connected layers. Date and H3 features are similar because what happens there is that each of them is divided in components. For instance, the date is divided in month, year, day of the week, and so on, hour and minute. And each of these components is embedded independently and then aggregated. H3, which is like a spatial indexing system, also has this notion of components. And when you get an H3 value, it's separated in components, embedded, and there's a weighted aggregation of that. I may have seen that there was a question.
There is a question, but it depends. We'll take the questions when you're ready.
So let me just get a second to the vector and then let's take the question. And then there's the vector feature. So you provide an entire vector as input. You can pass it through some fully connected layers and get a vector as output. So these are all the inputs that I have. So let's take a question now so that if it's related to the inputs, then I can answer that. So let me check. All right. We'll be able to explain use case for each CNN. So there's not real a use case in the sense that they are all swappable for each other. They may be useful for different things. So for instance, a stack of CNN can be useful, a deep stack of CNN can be useful if you're using characters because it basically creates representations layer by layer. The first layer creates like an aggregate of short n-grams of characters. The second layer may be a representation that looks like words because those are aggregations of n-grams of characters, and then it goes on and on. While the parallel CNN, for instance, is more similar to word n-grams. It's more shallow because it is only one layer, but you can set the width to be much larger, so you can have 4 grams, 5 grams, and so on. So depending on the use case, you may want to use a different encoders. Or for instance, the RNN can be useful if you have a medium range dependencies, in particular if you have the LSTM, where with medium range dependencies, I mean the even words that are separated in a sentence are important to be considered for making your decisions, for instance, for determining the class. And the transformer is even better at that, to have even more longer range dependencies, but they all come with their cost. Like usually CNNs are less expensive than RNNs, and RNNs are less expensive than transformers, for instance. All right, let's keep going here. So on the combiner, the combiner is important because if you have multiple input features, you have the output vectors for all these input features, and you need to combine them somehow. And the most basic combiner that is there in Ludwig is the concat combiner, which just takes these vectors, concatenates them, and then passes them from fully collected layers. And you can decide how many layers, what's the activation, and so on and so on, all the parameters that you want. There are other combiners in Ludwig that, for instance, exploit the sequence length time dimension, but those are a little bit more complicated, so I will not cover them here. But in the documentation, they are all explained. So if you're interested in that, you can take a look. And so what the combiner provides you is a vector output. And this vector output can be provided to the different decoders. And so the different decoders, what they allow you to do is they allow you to do different tasks. So if you want to have a regression task, you want to predict a number, then you can use the numerical feature. And all you have to specify, again, is just the name and the type. And all these gray parameters are optional, and they define how you obtain these predictions, these numerical predictions. In particular, one thing that you can specify is the loss. By default is mean squared error, but you can use mean absolute error and other losses. And also you can specify some fully connected layers that are specific to this feature and not going to be used by other features. Binary feature decoding allows you to do binary classification and is really similar to the numerical one. The only difference is that there is a sigmoid on top of the output to restrict it between 0 and 1. And also the loss that is used is cross entropy. Category feature decoding allows you to do multi-class classification. And in this case, you take the input vector, you project it to n dimensions, where n is the number of the classes, and then you have a softmax over that. The loss that you use here is softmax cross entropy, and you have a lot of parameters that you can play around with for like changing the weights of each class, or for instance, do label smoothing, or you can use negative sampling if you use a sampled softmax, and so on and so on. So you have all these parameters that you can play with. But again, those are all optional. All you have to specify really is the name and the type. SAT feature decoding allows you to do multi-label classification, where you don't want one single label for your data point, but you have more than one. And the way you do it is the same projection to n that you do with the softmax, the categorical classifier, but you do a sigmoid instead of a softmax there. And in this case, the loss to use is sigmoid cross entropy. You can also predict entire vectors, and the way it works is that you project to n, and then you can optionally have a softmax or any other non-linearity there. And you can optimize either by mean squared error or by cross entropy, depending if you did the softmax or not. This is useful for using, for instance, weak supervision labels where you have a distribution rather than a single label as output. Slightly more complicated is the sequence feature output, but it's really powerful. In particular because it's the only, for the moment, that has two decoders. One is a generator and one is a tagger. So let me give you some examples of those so that it's a little bit more clear what they do. So this is a tagger. On the left, you have the input sequence that you had. And so the tagger assumes that your input is a sequence. And what you have is that for each element of the input, you provide a classification output. So if the input has 5 elements, or in this case, let's say 4, you're going to provide a list, a sequence of 4 elements as output, 1 for each of the inputs. And this is useful, for instance, for doing information extraction like named entity recognition. If you have a piece of text that says Blade Runner is a movie, blah, 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 you can tag Blade and Runner as movie, is as O, which means I don't care, and all the other words with their tags, so that then you can say, well, within this sentence, there was a mention of a movie. The generator, on the other hand, is used for different tasks, and what it does is it takes an input, which is the output of the encoder, and then generates a sequence token by token, feeding the output of the previous time step as input of the next time step. And this is called autoregressive. This is, for instance, useful for doing machine translation, because the length of the input and the length of the output may be different. So you're not tagging each single word in the input with a word in the output, but you're generating a different sequence altogether. So this is why you may want to use a generator. Moreover, in some cases, some outputs may have dependencies between them. If that happens, you can specify a directed acyclic graph between them so that the output of one is fed as input to the other. This is a pretty advanced feature that I'm not going to cover in more detail, but you can find information in the user guide if you want to dive deeper into it. Now let's go to the last two pieces of the model definition. The training part is all optional, as you can see. And these are the default parameters, but you can change all of them. So you can change the batch size, you can change the number of epochs, you can change how many epochs to wait for the early stopping. You can change the optimizer, which type of optimizer to use, and all the parameters of that optimizer. You can also change the learning rate, and also the decay, the dropout rate, and if you want to reduce the learning rate when you do the performance plateau, and so on and so on. So you have all these parameters to play around with to customize your training loop. And finally, we have some pre-processing parameters. Some of them are generic, like you can specify how the data is going to be split if you don't provide your own splits. And by default, there's going to be 70% training, 10% validation, and 20% test. You can specify if you want to stratify this split, for instance. But then there are parameters that are specific for each feature type. So for instance, for text, you can specify the maximum length of the text in characters or in words, or the size of the vocabulary, so how many of the most common characters, of the most common words you want to retain, and so on and so on. So this allows you to customize your data pre-processing for text, and the same thing you can do for the other feature types. Now there is one additional caveat, is that these parameters are going to be applied to all the features of the same type. So if you have two different text features, they will all share these parameters for preprocessing. But if you want, you can also provide the same parameters when you define the feature as input or output, because you may want to have some different parameters for the specific different input features or output features. One possible example of that is if you have a news as input and you have actually two inputs. One is the news title and one is the news body. Well, for the news title, you may want to set the word sequence length limit to 500, and for the title, you may want to set it to 20, for instance. In particular, there's right now, Ludwig supports for text processing many different languages: English, Italian, Spanish, German, French, Portuguese, Dutch, Greek, Norwegian, Lithuanian, and there's also this multi-language tokenizer that allows to deal with when you don't know which language the input is. And these are all basically taken from the Spacey library, which is a really good library that we use for this purpose. All right, so before we dive into the examples, because there are some examples models on how to build some models using all this information they gave you about the inputs and outputs and the model definition, let me ask you if there's questions about the model definition.
Okay, so I'll just once again unmute myself and ask any questions. Okay, we will wait for a couple of minutes for any questions at this stage. I think the examples would be useful that people can see how they can utilize this in terms of what they're doing. So, okay, so far so good. So we can continue, I think, yes?
Sounds good. All right.
We can take the magic along, yeah.
Yeah. So this is again an example of text classification, the one that we've seen at the beginning of the presentation, where you have your data with 2 columns, news and class, and this is all the command that you have to specify for training your model. The architecture of the model is at the bottom, but as you can see, there is the model definition with the input features, a list with 1 element, name news and type text. And in this case, I added a little bit more parameters to show you. For instance, you can specify encoder parallel CNN and level word. And for the output feature, we have name class and type category. But now we can do also an image object classification, for instance. And your data looks like this. You have image path with the path to the images and class with the content of the class that you want. And as you can see, the model definition is almost exactly the same. The only difference is that the name now is image path of the input feature, sorry. The name of the input feature is image path, and its type is image instead of being text. And the encoder here, for instance, we're going to use a stacked CNN. The output feature is exactly the same as it was before. Here we have a speaker verification system that basically gives you 2 input audio files, and there is a same column that is, oh, that's weird, it's displaying it in Italian, sorry. Vero e falso means true and false. And so it's a binary output that tells you if the 2 speech files are from the same person or not. The way to do it in Ludwig is very simple. You have input features. In this case, is a list of 2 elements. One has name speech path 1, and it's of type audio. And the other one is name speech path 2, and is of type audio 2. And there's this additional keyword that we've never seen before, which is tide weights. In this case, tide weights speech 1. This means that the 2 encoders for speech path 1 and speech path 2 will use the same weights. So basically, we'll be using the same encoder, really. And then for the output, you have just 1 output feature with name same and type binary. And as you can see at the bottom, what you have is these 2 speech inputs that go into your input encoder, and then there is a hidden that you didn't specify the concat combiner, but it's there by default, and then there's logistic regression as output for obtaining same. This is another model, which is a simplified version of a model that we actually used at Uber for predicting the expected time of delivery of Uber Eats orders. The data looks like this. You have a restaurant with its name and an order that is a set of items. Actually, some items can occur more than 1 time, so it's actually a bag, not a set. And then you have the hour and minute when the order was submitted. Finally, what you want to predict is this ETD, expected time of delivery, which is the amount of minutes that it will take to deliver this order. The way you create such a model in Ludwig is you have your list of input features. The first one is name restaurant, type category, and encoder, for instance, embed. So we want to use embeddings for these restaurants, learn embeddings for these restaurants. And then we have the order. So name order, type bag, because as I told you, some elements may appear more than once. For instance, if I ordered 2 pizzas, 2 of the same pizza from the restaurant. And then another feature, name hour of type numerical and name minute of type numerical. And we want to predict the ETD, which is again a feature of name ETD, type numerical. And for instance, in this case, we want to use a loss, which is the mean absolute error rather than the mean squared error. An additional example is if we want to create a simple chit-chat dialogue system using a sequence-to-sequence model. What you have here is two users or two a user and an agent talking to each other. And so when the user 1 says something, the user 2 answers with something else. Hello, how are you doing? Doing well, thanks. So what you want to do is, given the input from user 1, you want to generate the output of user 2. In this case, the two sequences may be of different length, so you want to use a generator. The way you do it is you have one input feature, which is name user 1, type text, and in this case, for instance, we want to use an RNN as the encoder with cell type LSTM. And then you have the output feature, which is name user 2, type text, decoder generator. And also here we want to use the cell type LSTM, and we also want to use attention, which is a mechanism that allows you to generate, I wouldn't go into details, let's say it allows you to generate better text in most of the cases. And there's several different attention types. In this case, we will use attention button now, for instance. This is instead an example with sequence tagging. So you have an utterance as input. For instance, Blade Runner is a 1982 neo-noir science fiction film directed by Ridley Scott. And then we have a sequence of tags, one for each word in the input. So N is for Blade Runner. N and N are for Blade Runner and basically means noun. O means I don't care. D means date. So for instance, 1982 is tagged with D. And then all the rest I don't care. And at the end there's Ridley Scott, and I have tags P, which means person. In order to obtain this kind of predictions, what I have to do is really similar to the previous one, where we had the chief chat dialog model, where I have one input, which is utterance of type text, encoder RNN, and cell type LSTM, but I can use any other encoder if I wanted to. And then for the output features, we have the name is tag, the type is sequence, and here the decoder is tagger rather than generator like we did before. Cool, so these are all the examples. Maybe we can take some questions here before we move on to the next section.
I'll unmute myself now. So we have any questions here so far? If you can post here, yeah.
In the meantime, I will also tell you that on the Ludwig website, there's an example section with, I think, more than 20 different examples of several different tasks that you can do. So there's more examples there if you want.
Excellent. This is good. This is good. I think that will be very useful for this one as well. So any questions so far from anybody? I will just type here again. I have a question, actually, Piero. And the question is, I think that Ludwig is very interesting, but what is, okay, we got one more question from somebody. So I'll just go with my question first. And then, so do people typically use Ludwig for NLP, or do they use for other stuff as well?
So we have used it inside Uber for many, many different tasks, really. More than 15 that I know of. There's probably more that I didn't know of, to be honest.
But like what? Which are the most common examples of?
So many of them were NLP ones, but also, you know, the one that I showed you before for expected time of delivery.
Yeah.
We did something similar also for other parts of the for recommender system, for other parts of the company, like for freight. We were using it for tasks that were like prediction of sometimes prediction of time, sometimes classification, for instance, classification of queries, classification of customer support tickets, many different ones, really, many different ones.
Cool. Okay, so now we'll take Rigwet's question. So question is, okay, I got the question of Daria as well. So first we'll go with
encoders and decoders. Okay, yeah. So it depends on the type. So different types have different defaults. For instance, for text, the parallel CNN is the default encoder. But again, you can change that if you want. And also regarding decoders, most of the output features at the moment have only one decoder, so that's, you know, easy. For the sequence, I believe that the default default decoder is the generator, but you can easily change it to tagger if you want to. Let's see the second question. Are there any very special requirements to the data sets? Except it is a CSV. Example, classes can only be heavily imbalanced. Text should be cleaned out. Okay. So Ludwig does some, some pre-processing. As you've seen, you have all these parameters that you can control, but it's not really a heavyweight kind of pre-processing. So if you have really, really messy text, for instance, I would suggest do some cleaning before saving to the CSV file and then provide it to Ludwig. Regarding the class imbalance, there's nothing specific for the class imbalance. So for instance, if you have a really imbalanced data set and you believe that downsampling some classes or upsampling some other classes would be useful, you will probably want to do it before. Although Ludwig allows you to specify weights, different weights for different classes, which maybe, for instance, if there's a class that is really uncommon but is super important for you, you can upweight that class. So there's one potential way you can go around with dealing with unbalanced data.
So I have another question. Of course, if there are more questions from anybody else, we can take them. So you mentioned that there are some examples on the website. Yes.
Yeah.
And the question now is that our problem statement is that we have a series of effectively research papers, yes, based on COVID, and we want to sort of utilize, we want to use them somehow. Yes, or we want to summarize them, make it useful for subsequent researchers, analyze that, and so on and so forth. So if you can just run through, I mean, what I'm trying to tell you is just give us some hints, so that because Ludwig is a new tool for everybody. For many people, NLP is a new tool as well. Certainly for me it is, because I haven't used that much NLP in my work. So I think that so if I were to given this problem, and if I were to be given this effectively a tool and also some examples, so give us some hints on how we could kind of start from there.
Yeah, so again, I would go through the examples, look for something that looks similar to an idea that they may have in mind, but there's, I would say, if you think about what are the possible tasks that you can do, what I would say is, well, classification of sentences, for instance, or classification, if you have like all these papers, you can classify using their abstract and their, maybe classifying using the full text is a little bit difficult because the full text may be long. And so the models can have problems with that because of memory, really, more than anything else. But for instance, classifying using abstracts and the titles, it's totally doable, and that's one thing that could be useful for if you want to reduce them in some classes, then you have a tool for doing that, right? So that's useful. You can also think about building a question answering system where you take those articles, you separate them in sentences, and then those sentences are your answers, and then you can create a model that takes like a question and an answer and tells you if that true or false, and tells you if that's a binary output, and tells you if that answer is an answer to that question, for instance. So that's another thing you can do. Or you can take some text and you can produce some rephrasing or some summary of that text. You can use a tagger for doing that. You can use also a generator for doing that. Depends if you want to extract subparts of the original text or if you want to generate new text. Depending on the amounts of data, it may work, better or worse, depending on the amount of data that you have available. But that's something that is totally doable, for instance. These are the things that pop in my head, but there could be more, like multi-label classification can be useful. You can have, I don't know how many images are there in these papers, but if there are images that are important, then maybe you can also use those as input features for determining the classification of a piece of paper or something like that. Any sort of information extraction like this that you've seen here. I don't know if there are specific medical terms that are in the articles that you want to extract. You can have something like this sequence tagging that I'm showing you right now, and you can do something similar for extracting medical terms, for instance. These are the ones that pop in my head. There may be more, I guess.
No, this is good. This is the sort of thing I wanted for that people have some sort of guidance in which they can go and start to look into stuff. Okay, so any more questions now? We still take questions, another 5 more minutes.
No, actually, I'm not done yet. I mean, I have more.
Oh, sorry. Apologies. Then go ahead.
Go ahead.
Yeah. No, go ahead. Okay, then I will mute myself and off you go. Yeah.
Sure. And then I can take questions also at the end, right? All right, so the final part of the presentation is about also the programmatic API. So if you want to use Ludwig, you just have to do pip install Ludwig. It's very simple. And the programmatic API looks like this. So you just import this Ludwig model class from Ludwig.api, and then you provide you initialize an instance of Ludwig model by providing the model definition. In this case, model definition will be a dictionary that contains the same information that we have seen so far in all the examples, really. And you obtain a model object. On this model object, you can call train, providing training data either as CSV or as a data frame. And after the training, your model is trained, and you can use it for obtaining predictions with model.prediction on some other data, and you get the predictions. But also you can load some pre-trained model that you trained before with Ludwig model.load and the path of the model. If you have a pre-trained model and you want to serve it as a REST API, you just have to do Ludwig serve model path and the path to the saved model. That's all you have to do. There's a question, I believe. Let me check that. Oops, sorry. Can we use colonialism? Yeah, you can do that. So I think it's really great for experimentation in particular. And the reason is that you can easily plug in new encoders, decoders, and combiners and try different models very easily. And basically all you have to do is to change one string in your YAML file, and you have basically a new experiment ready to go. Ludwig also provides some visualizations, and these are, so the outputs are either in CSV or in MPy, or you also have these JSONs containing statistics. While training, because it's a TensorFlow model, you can also use a tensor board for visualizing and monitoring the training. But if you provide those outputs to these Ludwig visualizations, you can obtain these visualizations that are pretty nice. The first one is a comparison of performance of 2 models on different metrics. The second one is a calibration plot. The third and the fourth are plots that show coverage versus accuracy. The fifth is a comparison of the predictions of 2 models. And the sixth one is like F1 score versus frequency of the class. But there's many more. There's more than 20 different visualizations that you can play around with. So I'm working a lot on this version 0.3. I hope that I will be able to release it before the hackathon starts. If not, I will try to do my best. I cannot promise that, unfortunately. But let me tell you about the new features in version 0.3, because some of them you can already use them already in version 0.2. So these are a bunch of new features. Not all of them are entirely ready yet. The green ones are ready. The yellow ones are work in progress. The red ones are not there yet. So for instance, you have hyperparameter optimization, which is already there, but lacks the Bayesian optimization, which we're going to add soon. And then you can also train models in a distributed way with Hoverpod. You can deploy model using Neuropods, which is this new project announced today by Uber, which is like a way to deploy models easily. You can do k-fold cross validation. It's already there. And the vector type that I actually already showed you was a new feature in 0.3, but it's already available in 0.2 now. And then there's also additional improvements. So first of all, I'm going to port everything to TensorFlow 2 because right now Ludwig is based on TensorFlow 1. And this is halfway through. We're not done yet, unfortunately. And we also integrating with Hugging Face transformers to have some pre-trained models. Some of them are already there, some others are not. There are also going to be new pre-processing pipelines that people can plug in if they want. And also there's weights and biases and Comet ML integrations. And finally, there's also, this new custom model interface that is not there yet at all. Let me quickly show you an example of hyperparameter optimization. So what you have on the left is YAML example YAML of a model where you have an input text feature, an output class feature, and the training is a specific learning rate, a specific optimizer. And if in your model definition you provide these additional parameters, you can run an hyperparameter optimization. So you have to decide which metric you want to optimize. In this case, let's say accuracy, and the parameters that you want to optimize. For instance, the cell type of the utterance, or the learning rate, or training dot optimizer type, and also the ranges of potential values. In this case, for the cell type, you can say RNN, GRU, and LSTM. And for the optimizer, you can say SGD, ADAM, or ADAGRAD. And for the learning rate, you can say you want a float between 0.0001 and 0.1 in log scale. And you can say which strategy you want to use, if random, grid, or Bayesian. Bayesian is not there yet, random and grid are already there, and with how many samples, and also which executor to use, if to run this thing in parallel, or serially, or with Fiber, which is another project released by Uber, which allows you to run on a Kubernetes cluster. For training in a distributed way, all you have to do is you have to run the Ludwig command using Horovod run, and with Horovod parameters. For instance, NP tells you like how many parallel processes, in this case 4, but you can set whatever parameter you want. And in the Ludwig command, you just have to specify use Horovod. That's all there is to it. You can obtain a neuropod for serving just by running this command, Ludwig-m, Ludwig.neuropod, the model path and the output path for the neuropod. For running the k-fold cross-validation, you just have to add -- k-fold and the number of folds. And this is like an example of how to add a custom encoder. We will not get into these details, but you have to know that if you want, it's really easy to add a custom encoder or a custom decoder or a custom combiner to Ludwig. And they are not already all there yet, but you will be able to use all the encoders from transformers by just specifying either BERT, distill BERT, T5, Electra, and so on. The processing pipelines, these are not there yet, unfortunately. And if you want to use weights and biases or Comet ML, you just have to add -- 1 dB or Comet ML, and your models will be tracked on the training of your models will be tracked on those platforms for that makes it really easy for you to track the progress of your models. All right, so these are the next steps that I'm going to do. I'm going to add new features, more pre-trained input encoders, and also all the missing decoders, and the pluggable pipelines that allow you to, for instance, read data from Parquet, from HDFS. These are going to be my next steps. Cool, so here you have all the links that you need. There's the link to the documentation, to the repository, to the 2 blog posts, and to a white paper that I wrote. And these are the people that contributed the most to Ludwig, Jaroslav and Sai in particular, but also Jamie, Vilo, John, Doug, Patrick, Carlo, Chris, and Boris. Well, thank you for your attention. And if you want, I can answer more questions.
Sure. So thank you, first of all, Piero, for the great presentation, and that certainly is very useful. I have 2 quick questions. First of all, did you say that it was on Python, what? Python 2?
So this is all Python 3.
Python 3.
Yes.
Okay, then it's fine. So why I don't know why I heard this. Somewhere I thought you said with a different version of Python. Python 3.
Or maybe
Everything.
I may have said TensorFlow. So right now it's still on TensorFlow 1.
Okay,
I'm
okay,
doing
okay. Yes. Sorry. Of course. Yeah, TensorFlow, but that has no implications, isn't it? So it's pretty straightforward. We're just using Python 3 as we go, and
yeah,
should be fine. So okay. Second question is that we'll create a Slack group. I think, is that the best way for you and for everybody to communicate, or do you have any other recommendations?
Oh no, this sounds good for me. Yeah.
Sounds good. I thought so as well, because even when people start, I'm sure they will have more questions as they go along with that. So I guess the next thing is we're going to create this. We already have this corpus of papers, and we will create the problem statement. We will release the problem statement end of this week, so people can still join. Any new people can also join this group, because we'll record the video, we'll post it on the site, and if anybody wants to come from there, we still have enough time for them to get started. And then we go from end of this week. Indeed. Yeah.
That's good.
Very good. Very good. So any more questions before we wrap up? So thank you all, first of all, for attending. And I think it's a very powerful tool. I mean, this is very impressive. I mean, it is for more or less your initial personal effort. I think it's very amazing. And I recommended it to Oxford as well, because it has I like this fact that it's sort of a low coding base in a way, because it does so much with such a relatively less amount of coding. And therefore, it's a good way for people to sort of learn lots of new things quite quickly without getting too bogged down with stuff. Okay, so last time for any more questions. I will wait for a couple of minutes before we wrap up. Okay, here we go. So can we build MLOps?
What do you mean by MLOps?
Right. So MLOps normally in this context, I think what he means is that you build a model, deploy it into production, and then to validate the model and retrain the model if you need to. So this is the CI/CD portion. I mean, I know you mentioned Kubernetes a little bit and stuff like that, but I really don't think so, basically.
Yeah, no, so this is outside of the
that would be my plan.
So it would be like an outer thing, another loop, another wrapper that would use Ludwig inside it for doing all this.
Cool. Okay, so any more questions before we wrap up? I think we have still all the people here online, which is good. Number of people who started, everybody's still here.
Okay.
Any more?
You managed to extend the transformers. Also here, I'm not sure what you mean by extend the transformers.
Okay, we wait for him to, maybe I unmute him, or I can unmute anybody. We wait. So I'm going to try and unmute. I'm still not used to this. 1 minute. I'm going to, okay, sorry, he's typing something here.
So as I showed you, whenever you use a specific encoder in Ludwig, you have also all the parameters for you to play around with. So you can change the parameters from the regular input feature interface. So you put the parameters there, and they will go all the way down to the code that implements the transformer.
Cool. And this particular presentation, where is this? What you just presented to us now?
I think it's on my personal website. I will also eventually, I'm modifying the Ludwig website at the moment. It will be there on the Ludwig website eventually. At the moment, it's just on my personal website. But
okay, can you send it to me? I will upload it as well.
Sounds good. Actually,
yes, okay. You can send that to me wherever you want to, even in the chat is fine. I will upload it on the site. And also the other question is, that somebody asked me this before, is what is the best place to download Ludwig now?
Just do pip install Ludwig.
No, but where to download it from?
So if you do pip install Ludwig, it just
I see. Okay. All right. Sorry. Pip install Ludwig. Okay, fine. Then that's good. So it's not like, because you remember the GitHub repository change, we don't need to go anywhere near that.
Yeah, you don't need to do that. But yeah, it's also, I mean, there is the link to the, sorry. Here, there's the link to the old GitHub repo. Let me write here.
Yeah, because some people went there, you see, and they asked me this question as to how exactly do we get started with this? And that's why I think that's great. So the fact that it's a pip install, that's good.
Yeah. Also, the repository is actually still there. You will move soon enough, because this is, again, not public yet, but Ludwig, we are in the process of donating Ludwig to the Linux Foundation. So it will change, will not be uber.github.com. It will be like ludwigai.github.com. But it's not, we haven't transferred it yet. We already transferred the documentation. So the documentation is, but we also changed ludwig.ai to point to the new documentation. So you will find it there easily.
Cool. So I think Gareth is saying that it took seconds in the terminal, which is nice. So that's good. So installation.
Yeah. Also, there are some dependencies, so it may take a little bit longer. Just because
yeah. But that's good. That's good. You know, I mean, that's really what we wanted to get to, because few people asked about the sort of repository they could go to, but what you're saying is we don't need to go anywhere near that at all. Just directly do pp install.
Yeah. I mean, if you want to play with the repository, it's just on GitHub.
Yeah.
Just search for Ludwig on GitHub, and you will find it also.
Yeah.
So you can do whatever you prefer.
Yeah, but the ideal way to get started is pp install.
Yeah.
Okay, very good. Okay, then I guess we are wrapped up for now. I think this is great, and thank you again. I will post the video, I will post a recording, and also I will post your slides here from this link. Yes, and yeah, thank you again. We'll post the Slack, and off we go next week. Very good.
Thank you, everybody. I'm
okay, thank you.
What people will come up as projects in the hackathon. I'm pretty excited about it.
Thank you. Thank you. Thank
Bye-bye.
you again. Thank you. Bye-bye. Bye-bye. Bye.